Sure. Okay, we're going to start back up. I'm actually giving the first half of this talk, and then Scott's going to jump into the second half. We'll start with my own camera. Okay, so we're going to talk about our team approach and heavily focused on semi-autonomy and our various capacities to stay on track for that, and I think we'll be dedicating ourselves. It was initially, and has been for many years, the approach that Seth Seller has taken. Obviously, for the last week and a half, we've had some incredible news about Seth. He was the driving force of putting together a team, and we just wanted to acknowledge what has happened in the last week. Together with Russ, put together a very significant team, and we're really hoping in the next year to year and a half to capitalise on all the work to kind of push in the direction that he had been working on for the last 10 years as well. I'm going to try and touch on some of the work that various people in this photograph have done in the last year. But first, to quickly acknowledge that we finished fourth in the competition, got half the points, averaged 2 points per task. But primarily the things that we learned in the competition were being compelled to focus on these tasks. We were exposed to the limitations of our system. I think, we split on a task basis, so different individuals in our team did different tasks and came up with very different solutions to different tasks. And I think they came back with lots of some positive, but lots of negative feedback about, say, the limitations of our user interface, maybe missing capabilities in our planners, and how that limited us from being able to stay on track with the semi-autonomous approach. Which, in the initial proposal, we had this concept of a very minimal user interface, just we suggesting suggesting contact points, say, with the climbing task, which we went ahead and sort of implemented. Our planner could support it, we could just drop footfalls, drop arm reaches, but I think there was a gap between what could be executed there as we tried to push up in that semi-autonomous direction. We assumed significant kinematic calibration, which at the outset with the robot we did not have, and sensing accuracy. And I think it's been a winding road as we pushed back over the course of the trials, and then since the trials to stay on track with that. We had the same system architecture as most teams, so let's touch upon it. A multi-process architecture spread across multiple machines, and multiple operators, and all the simple or the common data compression of LiDAR and image compression. In addition, we also had to probabilistically compress our robot plans. We transmitted full robot plans for every sequence from the base to the robot, so that was one of the difficulties that we had to deal with coming into the trials. But in general purpose tools that were deployed in multiple cores was one of the key building blocks of our system. Again, as some of the other Atlas teams touched upon earlier, we started off with the robot for a 5-month period and had to characterize the hardware, learn the limitations of the sensing suite. In this case, one of the major things that we did was improving the calibration of the LiDAR, and improving the calibration of LiDAR to camera, so that we could try and get back to that operation of the robot as semi-autonomously on a higher level. In addition, we also learned about what the robot could or couldn't do. So you can see the sensor field of view of the camera system, the little black line, and then you can see hotspots of where the manipulation area of the robot was. So between the calibration of the sensor data and where we could actually sense, it required a significant amount of modification of how we were intending to do it. I don't think we gave significant consideration to range of motion limitations, and as a result, I think one of the key things that we did in the development of our object-centric planning system was the assumption that execution of sequences, having been specified to the planner, would be straightforward. So while we have general purpose and optimization-based reaching planners that are grounded in objects, so we're reaching to objects, we're moving objects in our user interface, the reality was that when we were executing with significant issues with our kinematic calibration, there was a tendency as a competition approach to tend towards pre-scripting, to build in the tools that we had originally avoided. In addition, there were some other positive attributes we had to add to our system, including relaxation of reaching constraints. So you can see this is a reaching goal here, and the reaching planner is relaxing the reach so as to be able to get as close as possible, or to move that region goal so as to achieve a less satisfactory goal, but one that could actually grasp that piece. One of the key building blocks we built for the trials was our fitting, and even though it's very, very basic, and I think it's very much a bottom-up approach, we had focused on ICP or mesh model to mesh model alignment, but in the end, for the trials, we rolled our own, or Pat Marion built a system that used simple filtering chains that use assumptions about the tasks. So in this obvious case here, you can see an assumption of a table, and then finding from the point cloud that lies on the table the drill. And when that's paired with a user interface, we focused on being able to very minimally provide the input so that the user could click and drag across a 2x4, provide the information that it's a 2x4, and then out pops the object fitting, so that the object fitting algorithms were very quick, as you can see here, but the user interface was very straightforward. Another example, a valve and a lever on a wall, finding through, these are also coded in Python, so reconfiguring of the different tool chains is very straightforward. So finding the floor, removing it, finding the valve wall, finding the points in front of the valve wall, and then running two fitting algorithms to return the objects of interest. So that was how far we were getting with just defining objects of interest that were then exposed to our planning system. And we're going to focus on two of the specific tasks from the challenge to illustrate some of the things that we thought we got right, as well as some of the things that Scott's going to explore about what we're trying to do for the next stage. So in the drill task, as Patrick mentioned, there was a necessity to have a drill in a hand that has a gaze constraint to execute a motion. So you can see here illustrated there affordance of the cutting pattern, which could be specified online and by the user interface, and the affordance of the drill in the hand, and those were the inputs. The location of that drill pattern and the location of the drill in the hand were the inputs to the planner, which we actually ran online. So we didn't script the drilling sequence, but what we did do was we produced this composite map, this hypothesized map by producing a planning, a hypothesized plan which solves inverse kinematics across a set of sample points on the drill target, which returns to us both that the problem is feasible with the robot in one single action, as well as the information about where to stand, which also took into account that the task should generally be done in front of the robot. Given that information, then we could step to the application and be confident that we could do the task from the application. I think that's one of the key things that, as we go forward to the next stage, we're working towards implementing as much as possible this envisagement of how we're going to execute a task without actually having a drill bit cutting into a wall while we're actually figuring out if we can move 5 more centimeters to the right. In addition to the positive things from that, the actual execution still needs to be improved. The execution of the drilling pattern, this is a pretty complicated slide from our JF4 publication, but the execution of the drilling sequence here, while it's illustrated as one complete section, was actually a series of user inputs to continue on each step. So while we were automatically continuing along this triangle pattern, the user was still required to keep track of whether we were going outside the bounds, whether we were building a force on the robot. So as we go forward, as well as trying to reconsider our user interface, we also want to look at more compliant whole body control. We're also very interested in walking and locomotion. In the walking task, or in walking in general, we took the pragmatic decision that the BDI walking controller was capable. We did have our own background in this, but given the time frame, we chose to use the BDI walking controller paired with our own footstep planners. So our footstep planner could reason about an optimally minimal set of footsteps to go from goal A to goal B over uneven terrain. What it didn't have was the capability to support discrete locations, so footstep patterns in the terrain. So we used the footstep planner paired with BDI, but in the case of the terrain pattern, the terrain course, we fell back to manual footstep placements. This is one of the things that Robin Dietz, who's been developing this planner, is now focusing on. We want to be able to support minimal user input to produce an optimized footstep plan that can go over uneven terrain. this is an illustration of the footstep distributions from the task. So this is the amount of time taken to execute or to plan a two-step plan and then to execute it. So planning time and execution was pretty much the same, and we were executing 2 steps at a time. Every team that had an atlas, I think, was executing 2 steps at a time. And we want to look at how we can improve state estimation and execution to speed that up. So I'm going to hand over to Scott after this slide. But our lessons that we've drawn from the competition are that while we had a planning-heavy high-level approach, I think we do a lot better in delivering that for the competition. As we got closer to the competition, more scripted motions had to be introduced. And while we implemented a very inefficient type of teleoperation for certain tasks, it's unsustainable for daily development. So we're refocusing ourselves towards the competition. And maybe this stage I'll let Scott jump in.
Thanks. So I'm going to talk about more of the sort of little technical chunks that we're working on now to try to address some of the drawbacks that we saw in our system for the trials, but also kind of just because we think they're really cool research problems to be working on in general. So as Maurice said, Robin Dietz has been responsible for our footstep planner from the beginning, and sort of at each stage of the competition we have a great footstep planning engine. But he's looking to push that further so that we can have a sort of more general, collision-free footstep planner. So if you were to just write down this kind of general collision-free footstep planning problem, it's non-convex and in general quite difficult to solve. So Robin's idea is instead of trying to avoid obstacles, he's going to solve an efficient optimization to compute these convex safe regions, sort of in the configuration space of the foot. And then the footstep problem, planning problem then becomes one of assignment of footsteps to these convex safe regions and optimization of the placement of the foot within these regions to minimize some cost function while respecting the kinematic reachability constraints of the robot. So here's a simple example that Robin's cooked up. We're planning this motion, walking from this block to this block, and he says, just go here, and the footstep planner does this analysis and generates a feasible footstep plan, and then Robin deletes a block, and the robot has to take this more circuitous route around because the planner realizes that due to its kinematic constraints, we cannot actually achieve this kind of footstep. And of course, we can do the same kind of thing with the real robot. So here's LiDAR returns in our lab with some center blocks up in front, and Robin's able to compute these convex safe regions and plan footsteps onto the blocks and around the blocks and so on. So given the output of this footstep planner, we ultimately have to turn this into a robot walking where we want it to go. So our approach to do this has been one where we're sort of considering simple dynamical models of the robot. So for example, we just think about the center of mass dynamics and take these footsteps and we define the center of pressure or ZMP trajectory through them. Then we can exploit the fact that this dynamics is so simple and we can solve efficiently optimal control problems for this simple system. So our approach has been to use TVLQR design to stabilize the center pressure dynamics and use the optimal cost to go from this solution as part of an objective in a quadratic program that's going to compute inputs for the full robot while reasoning about the instantaneous dynamic contact and input constraints of the system. And we've also thought a bit about how to do this efficiently. So we really want the stabilized control for the robot to run quickly, okay? And so we've come up with this a custom active set algorithm that exploits the temporal structure and the inequality constraints of controllers like this, not just the specific controller that we've implemented, but many general sort of QT controllers of this sort of general class, and we're able to achieve very high, 1 kilohertz control rates for Atlas. And so this is the approach we use in the VRC, and it turns out that using these same ideas, we're able to achieve stable dynamic walking with Atlas, which is cool. But of course, it's not to say there wasn't some significant hardware challenges along the way. So people who have tried to do this kind of thing in Atlas will know that there's a lot of sort of pesky things like significant joint friction up to 10 newton meters in some of the joints. There's no direct joint force sensing, which makes it hard to, for example, close a loop on force. There's backlash in several of the joints, and in the back and the legs there's no output joint position sensing, so we can't really directly sense this backlash at the joint level, so we maybe only know where our feet are to within a couple centimeters. And so the way that several teams, and I think IHM2 will probably talk about this as well, have sort of converged on achieving good tracking control is to sort of do combined feedback on force and velocity, or even force, velocity, and position. And in doing so, you kind of, to some extent, sacrifice compliance. So, as Maurice mentioned, another sort of thing that we felt really kind of slowed us down at the trials was drift in our state estimator. So this required us to do things like to only plan 2 footsteps at a time, or take time to refit objects to the LiDAR data as our state estimate is drifting during manipulation. So Maurice has been doing a lot of work this year on improving our state estimation. And the way that he's doing this is inspired by work that's actually done in fixed-wing aircrafts. And you combine inertial, kinematic information with stereo depth information and LiDAR point clouds, and you can do really cool things. So Maurice has built a drift-free state estimator for Atlas. Okay, so here we have these accumulated point clouds to build a 3D model of the world. He's fusing all of these sensor sources together, and you can do things like plan footsteps over cinder blocks, okay, execute them, and the robot has a very small close error throughout that execution under 2 centimeters compared with motion capture data. And then, when you get to the other side, you can just replay those footsteps in reverse because the state estimate just doesn't drift. Okay, we've not added any rear-facing sensors to the robot here. So we think this is really going to change the way that we execute walking plans in the next phase. So one part of our system that's been great pretty much from the beginning is our whole-body motion planning engine. So here we have great tools that are freely available for solving nonlinear optimizations to do whole-body kinematics planning, single shot, and also kinematics trajectory optimization. And they run at interactive rates. So here's a user grabbing on the Atlas's hand in our interface and jerking it up and down, and the planner is responding basically instantly with whole-body reaching plans. And since the trials, we've also incorporated collision-free motion planning. So this has been the work of grad student Maurice Fallon, and it's taken this idea of nonlinear optimization-based motion planning and exploited tools from Bullet so that we can add constraints that ensure collision-free motion. And on sort of the cutting edge of things is we're taking now this idea of doing full-body kinematic motion planning, which we can do very efficiently, and this idea of using simple models of the robot's dynamics to generate dynamically feasible whole-body motions through contact. Okay, so this is kind of a fun example. This is the work of Hong guy and Andres Valenzuela, and this is sort of a recent thing where they've gotten the robot to jump up and monkey bar across and jump down. So this is kind of sort of a fun example, but we think this is seriously going to be a tool that's going to allow us to do things like get up from the ground and exit the vehicle in the final stage of the competition. So putting all this together, the sort of final thing that we're really trying to do is make the system more semi-autonomous. So the idea here is in the trials, the robot relied strongly on the user giving it actions to do at every step of the way. So we tell it to walk up to the drill, and then we tell it to grasp the drill and pick it up and walk over to the wall. Where we should really be able to inject some of that procedural knowledge into the robot to relieve the burden on the operator. So the idea is you can give the robot some high-level task description, and it can generate an extended motion planning sequence that the user can review and say, yes, go ahead, do that thing. And then we endow the robot with predicates so they can evaluate its execution of these motion plans to know that it's within the initial condition set of its subsequent plan, or if it needs to stop and ask the user, what do I do now? I don't really have a way to get out of this situation. And we've been sort of trying these ideas out in the lab. So here's an example. So there's Pat Marion in the back. And in this example, he's clicked the mouse button once, and the robot has this finite state machine that it's executing. So it's generated this long sequence of plans. It's evaluating each segment of the plan and it's determining whether it's succeeded or not. And the task here is just to grab, localize and grab these little PVC pipes off the table, back up and chuck them into the bin. And we have other examples where we're doing the valve task over again. I'm not showing just for time's sake. we're able to just sort of proof of concept that we can do the valve test significantly faster with this kind of tool than relying on careful human interaction with the robot. And here's just another example of the sort of one-button style demo where the robot's actually localized this board on the ground. It's using our own state estimator, our own walking controller, whole body motion planning, all the tools that I just quickly described. To walk up to this board, it's going to stand there for a second, wait for the LiDAR to do a single sweep, localize the board, reaches down, picks it up, and then it just keeps dropping the board over and over again in front of it and reaching down and picking it up. I think we need to get an Atlas-shaped T-shirt maybe here that says Local Mile No Extenders. But this is the kind of cool thing that you can do when you have a good balancing controller and the ability to generate whole body motion plans. It's actually not very hard to pick things up off the ground. All right, I'll go back to this video at the end for questions if you guys want. But just one final thing. So many of the things I've talked about, the footstep planner, the whole body motion planning, collision-free, all that stuff, the balancing controller, the general QP solver, all these things are available in Drake, which is a software package that's been developed over the past few years in the robot locomotion group at MIT, but it's now a sort of growing thing. We have people from all over the place joining up on GitHub, adding code, and it's a really active user community. And so I encourage you guys to check this out. Try things out, load your robot in, try our planning algorithms. Yeah, submit issues if you find anything you can't install or so on. But yeah, that's it. I think I'll stop and we'll leave this playing while we go through questions. All right, any questions? Yep.
You talked about the localization, drift-free localization. How well does that work in an environment where you don't have a lot of objects in front of you, like a wall or a gantry or something like that?
Yeah, more on that one.
So your low drift localization, in your demonstration, there were a lot of features directly in front of the robot. How well does that work if you have more open space?
I wish we had lots of open spaces to test it on. And it is stable to significant changes in the orientation. So I didn't include it in this video, but there is a demonstration of it creating a knockoff facing in one direction and turning 90 degrees, and it's still stable in that environment. I think it's obviously necessary that there's going to be some physical structure. That's how it's getting its constraints. But I think that you're looking at 30 meters range and a big high bay there, and you don't really hit 30 meters. I can't imagine us operating the trials. We don't have anything in that vicinity. And then the corollary is if you don't have anything in the vicinity like that, you might even need this algorithm.
Yeah.
You mentioned that the one-button operation was substantially faster than the teleoperation. How is that? Do you have a rookie teleoperator, or is it an experienced teleoperator?
Oh.
And is it close to a tie, or is it a big difference?
So it might be a fact of how we're actually teleoperating the robot. We haven't designed the most efficient teleoperation interface. That was more, as our goal from the beginning is to do this motion planning based thing. We give high-level instructions to the robot and then execute it. So the teleoperation interface that we had was sort of an addition right before the trial so that we could do things. But the way that we were turning a valve is pretty manual. So we put the hand in the valve and kind of turn it along this way. But if we do a sort of automated sequential motion planning thing, the robot just walks up to the valve, generates circular motions, and that's just faster by a lot. So we did, what was it, like 5 or 7 minutes or something like that?
It was less than that, it was 3. But I would say, in terms of teleoperation across the communication links that we've been exploring, the reaction time of the user just to this new sensor data and then making decisions, I think there must be an upper bound on how well they can do. I'd say the shaft team clearly got very close to that upper bound. They were very refined. They did still take 30 minutes to do a lot of the tasks. So if you want to go quicker than that, I would suggest maybe we can be proven wrong, but I would suggest we need more time.
Thank you.
All right. Okay. Thank you very much.
Thank you.